Okay. So up to last class, we have completed impulse, right? On Monday, we have completed impulse. After impulse, the next topic is common forces in mechanics. It's basically the most important topic of laws of motion, where we will study pulleys, system with strain, system with masses in contact. So this starts with the concept of common forces in mechanics. Common forces in mechanics. This we have already discussed in this common forces in mechanics. We have discussed by doing work, energy, and power, but I am repeating it again. The first one is weight. Weight we did in very much detail. Like weight is the gravitational pull of Earth. The gravitational pull of Earth is weight. So if you have a body of mass m, the force with which Earth pulls this body is its weight. So weight acts in downwards direction. The weight of the body's mass multiplied by acceleration due to gravity. So this is weight, which is equal to mg. After weight, the next force is normally action. This too we did in work, energy, and power. Normally action. Normally action, it is a contact force. Contact force which act between bodies in contact. So this is the force which act between two bodies when they are placed in contact. Let's say you substitute placed. This is a surface. Over the surface, I placed a body of mass in. So due to the contact between the body and the surface, a contact force which is known as normal reaction will act on the body. See some examples of normal reaction. Like if I place this pen in air, it falls downwards. If I place this pen in air, then this pen will fall downwards. Why it's going downwards, Sanya? Which force is pulling this pen in downwards direction?
Gravitational.
But if I place this pen over my hand, no, it's not going anywhere. Why? Is gravitational force not acting on the pen now? Yes, it's gravitational pull of Earth is acting on the pen even if this pen is at rest. But the net force over the pen is zero. That means there is one more force which is acting on the pen, and that force will balance the weight. I'm repeating again. If I place this pen over my hand, then a gravitational pull of pen is weight. Gravitational pull of Earth which is known as weight, is acting over the pen. Earth is trying to pull this pen in the downwards direction. It is acting. But along with gravity, there is one more force which is known as normal reaction that is acting on the pen, and that normal reaction balances the weight. That's why this pen is not going in downwards direction. In laws of motion, there is just one rule. If a body moves, that means some force is acting on the body. If body moves with constant some acceleration, that means a force is acting on the body. Body cannot move by itself. But if a body is at rest, that means net force acting on the body is zero. I'm repeating it again. If a body is in motion, particularly accelerated motion, then some net force is acting on the body. If a body is at rest, That means net force on the body is U. When this pen was in air, if I release this pen, then this pen is going downwards. This simply means that gravitational pull of Earth, weight is acting on the body, which is pulling this pen downwards. But if I put this pen on my hand, then along with weight, my hand will exert a normal reaction over the pen, and the normal reaction will balance weight. If I take the case of this mass, its weight is acting in its downwards direction, but this surface will exert a normal reaction on the body in upwards direction. And this force is known as normal reaction, which acts between bodies in contact. There's one more thing. Direction of normal reaction is perpendicular to plane and towards the body. It's perpendicular to the plane and towards the body. That's the normal reaction acting on the body. So wherever you have contact between two solid surfaces, you will have normal reaction. The contact could be in this way, or the contact could be in this way. This is also a type of contact. I take this body, then I take another body, place them in contact. This is body A, this is body B. This is one normal reaction in one. This is another normal reaction. These normal reactions are acting on the body when they are placed in contact. It always acts perpendicular to the plane and towards the body. If your body is placed in this way, this is x-axis, this is y-axis. These are two surfaces, one horizontal and another vertical surface. And we have placed the body in this way. So here you have two contacts. One here, another here. So if you have two contacts, that will mean two normal reactions. And the directions of both the normal reactions are perpendicular to the surface and towards the body. Normal reaction on A is in this direction, this is A. Normal reaction on B is in this direction, that's A. So both the normal reactions are perpendicular to the surface and towards the body. These are the directions of two normal reactions. So the number of normal reactions are exactly equal to the number of contacts. So that's about normal reaction. And remember one more thing. Normal reaction is electromagnetic force. Normal reaction is electromagnetic force. There's an electromagnetic force which acts between the molecules, the electrons and protons of the surface and electrons and protons of the rod. That's the force which is acting in between is normal reaction. It's electromagnetic. It's basically due to electron and proton interaction, this normal reaction. Third is tension. So tension is basically a force with which string pulls. So tension is the force with which string pulls. String pulls. Its direction is along the string and away from body. So tension is a force which acts along the string. Its direction is along the string and away from the body. Like if I take this string, it's in string. So I'm taking this string and I connected a mass with this string. I simply connected a mass with this string. So the force with which this string pulls this mass is known as tension. If I'm taking, consider this as mass and this is the string. A rope, a wire, a thread is a string for you. So if I'm pulling this mass upwards, I'm not directly applying the force on the mass, I'm applying force on the string, then string is applying force on the mass. So the force with which string pulls a body is known as tension. Okay, can you just tell me in which direction the tension is acting if I am pulling this mass upwards? I need answer of each one of you. If you don't know, just write don't know. If I'm pulling this mass upwards, can you tell me the direction of tension force on the mass? I'm pulling this mass in upwards direction. Just tell me the direction of tension force on the mass. Is it upwards, downwards? I'm pulling this upwards, pulling this mass upwards. Tanya, Fazil, upwards. Very good. So this is the case. Like this is string and this is mass m. If I'm taking this mass upwards, then string will apply a force on the mass in upwards direction, and the direction of that force is tension. The name of that force is tension. It's acting in upwards direction. So this is tension which is acting upwards. So tension always acts along the string and away from the body. It's acting upwards. If instead of this string, I take another body, like I take this body of mass in, I connected this body through a string and I'm pulling this string in right hand side direction. So again, this string will exert a force over the mass, tension, which is acting in downwards, rightwards direction. So tension always acts along the string and away from the body. If I connected this string to the left hand side, then the tension will act in the left hand side direction. Tension always acts along the string and away from the body. Few more examples. Okay, so that is about tension. This is electromagnetic in nature. This force is again electromagnetic in nature. It acts between electrons and protons. This is electromagnetic in nature. Now we have some approximations for the problems of string. Let's have some approximations for strings. For the problem of strings, we will use some approximation. We will approximate that your string is massless. In numericals, unless the mass of the string is given, we will always consider your string as massless. If your string is massless, then tension, first approximation, tension in each part of string is same. Tension in each part of the string is same. Like say you take a string and you took two masses. You took two masses and a string. Let's call this as mass M1. Let's call this as mass M2. So this is string. This string must be exerting some force over the mass M1. So the direction of that force is right hand side, that's T1. Force over mass M2 by the string is to the left hand side, that is T2. If a string is massless, then T1 is exactly equal to T2. So if you have one string which is massless, then tension in every part of the string would be same. Tension will not change. That's the first thing. But if you have two different strings, like I take this as mass M1, I take this as mass M2, and I take this as mass M3. So now you have three masses and two strings. So the direction of tension is along the string and away from the mass. So this is T1. On M2, the tension will remain T1 only because it's the same string. But this is a different string, so tension would be different. This is T2 and this is T2. Now T1 may not be equal to T2. T1 in general T1 is not equal to T2. This is one string, this is another string. So you have two different strings or two different tensions. But this is a single string. In a single string, you will have same tension. But for this thing, you should have a massless string. This is valid only for a massless string. Next. The second approximation for a massless string is, if you have a massless string, then acceleration of all the masses connected by a string is same. Acceleration of all masses connected by a string is same. But for this property, your string should be inextensible. Or I should write this as, if string is inextensible, then acceleration of all masses connected by the string is same. Inextensible means the total length of the string is constant. It cannot stretch. If a string cannot stretch, then acceleration of all masses connected by the string would be same. So you can take this as you take three blocks, connect each block by a string, this is M1, this is mass M2, this is mass M3. All boxes are connected by strings. So if all these strings are inextensible, so you have two strings basically, string number 1 and string number 2. If both string number 1 as well as string number 2 are inextensible, if they don't stretch, then all blocks will move with the same acceleration. Acceleration would be same. For this condition should hold, that string should be inextensible. So these were three important forces. The first one was weight, second normally action, third strain. After these forces, you should know how to draw free body diagram. Free body diagram. See, usually in problems of laws of motion, in problems of dynamics, you have multiple bodies. The system is very complicated. It's a very involved system. Like in a single numerical, so you can have a surface. You can have multiple blocks, one over the other. You can even have pulleys, multiple pulleys. You can have another block which is connected through. So you can have multiple blocks, multiple pulleys. So to solve this system, there are two ways to solve the system. Either solve the system by considering all masses at once, or you can solve the system by taking one mass at a time. Like if in this system I have mass number 1, mass number 2, and mass number 3. I can either take all mass 1, mass 2, mass 3 together and can solve the system, or I can solve them separately. Like it take mass m1 separately and solve it. Solving mass m1 means calculating all forces on m1 as well as acceleration of m1. Solving here means calculating forces and accelerations. I can solve mass 2 along with the whole system, or I can solve mass 2 separately. Like I draw mass 2 separately and then calculate the acceleration and the forces acting on it. To draw these masses separately is known as free body diagram. Free body diagram means you free the body from the system and then solve it. This is also known as FBD of the system. So there are certain rules for making FBD. Rules for making FBD. The first rule is isolate body from the system. That's the first rule. The second rule is apply all forces which are acting on the body by the system. Apply all forces acting on the body by system. There's one important thing, that while making FBD of a body, we consider only those forces which are acting on the body. Forces applied by the body are not considered in FBD. Forces applied by the body are not considered in free body diagram. So while making FBD, we consider only those forces which are acting on the body by the system. But the forces which are acting on the by the body are not considered in FBD. Let's see one example. This will make things very clear that how to draw an FBD. So this is a surface. So two masses, mass m1, mass m2. This is a support from which I have connected a string to mass m2. This is my entire system. So before drawing FBD, I have to mention all forces which are acting on the body. So can you just count the total number? Just draw this diagram. I'm giving you 2 minutes. Draw this diagram in your notebook and try to decide the total number of forces which are acting on the system. Try to decide the total number of forces. You knew weight, you knew normal reaction, you know about weight, tension. Just try to calculate the total number of forces which are acting on the body. Let's start with mass M1. So the forces which are acting on M1 is, first is weight of M1, which is M1G. That's the first force. Then the normal reaction which is acting on this mass M1, I call this normal reaction as Na. I'm saying it Na. This is the normal reaction on M1 by the surface. Then you have another normal reaction Na. This is basically the normal reaction which this body is acting on the surface. Because forces are always in action and reaction pair. If surface applies a normal reaction on the body, then in turn, body will apply a normal reaction on the surface. So this Na here is normal reaction on M1 by surface. This M1G is normal reaction on mass M1 by surface, not surface, by earth. Here this Na is normal reaction on surface by M1. This is normal reaction on surface by M1. Similarly, if I take body 2, these all are, and there's one more force which is acting on M1. This body 2 is applying some force on M1. I call this force as MB. So if M2 is applying a normal reaction on M1, then M1 will apply a normal reaction on M2. So this MB is normal reaction on M2 by M1, and here this NB is normal reaction on M1 by M2. There is one more force which is weight of M2, which is basically M2G. M2G. There is one more force. Since this M2 is connected by a string, the string must be pulling this M2. String must be applying a tension over this mass M2. That force is known as tension. So these are the forces which are acting on the system. So if I count the total number of forces, 1, 2, 3, 4, 5, 6, 7, 8. So you have total 8 forces. Okay, now if I ask you to make FBD of, let's say I'm asking you to make FBD of M2. Okay, now just count the forces which are acting on M2, not by M2. Just count that this is tears, tension on M2 by string. So the whole system is, I have drawn the whole system. First one, second one, third one. Isn't there any? Yes. Right, 3 forces. So in FBD, while drawing FBD, you will consider only these 3 forces. So this is your M2. Tension T is acting on M2 in upwards direction. M2G is acting in downwards direction. This is FBD of M2. So these are basically the forces which are acting on M2. Okay, now just tell me the number of forces acting on M1. See, I don't consider this force. The reason is this is not on M2, this force is by M2. Now consider, tell me the number of forces which are acting on M1, FBD of M1. One force, second force, third force, right? Three forces are acting on M1, right? So the first force is weight, M1G. The second force is normal reaction, which is acting upwards, it's Na. Third force is normal reaction, which is acting from the top end. So this is how we draw FBD. So while drawing FBD, we consider only those forces which are acting on the body. After this free body diagram, the next is equilibrium. In mechanics, equilibrium means the net force acting on the body is zero. Right now, I am considering equilibrium of a point mass. I am not considering a rigid body. Rigid body means a body having a definite shape or size. I am just considering a point mass only. I am considering only translational equilibrium. Translational motion means straight line motion. Right now, I am not considering rotation. I'm not considering the motion of a fan. Fan is rotating. I'm not considering rotation. I'm just considering straight line motion. Straight line motion is known as translation. So in mechanics, equilibrium means a body is in equilibrium. Is in equilibrium if net force acting on body is zero. If net force acting on a body is zero, then you will say that your body is in equilibrium. So if you have this body, and let's say three different forces are acting on the body. So this is force F1, this is force F2, this is force F3. This means force F1 plus force F2 plus force F3 is equal to 0. This is equilibrium. Equilibrium means the net force acting on the body is 0. F net is 0. Now, if net force acting on the body is 0, then you can say that acceleration of the body is 0. Because acceleration is force upon mass. Acceleration A, which is net force divided by mass, is 0. So if the net force acting on the body is 0, that means acceleration of the body is 0. So acceleration is 0, that means if a body is in equilibrium, that means acceleration of the body is 0. Next, we can do some type of equilibrium. You can have two types of equilibrium. Your equilibrium could be static. It's a type of equilibrium. So above two conditions will hold for both of them. Your equilibrium could be static or your equilibrium could be dynamic. Static equilibrium means net force 0 because the type of equilibrium. Acceleration 0 is a type of equilibrium and body is at rest. Dynamic equilibrium is again a type of equilibrium. So first two conditions should hold. Net force is 0, acceleration is 0, but your body is not at rest, your body is in uniform motion. Body is in uniform motion. So these are the two types of equilibrium, either static equilibrium or dynamic equilibrium. Equilibrium could be static or dynamic. Static means net force is zero, acceleration is zero. Dynamic means net force and acceleration is zero, body is in uniform motion. Let's do some basic problems on equilibrium. The first question is, so you have three strings, you have to calculate tension in each string if your system is in equilibrium. So let's name this point as point P. So first of all, let's consider this mass M. So how many forces are acting over this mass M? Can you decide the total number of forces acting on it? One is weight mg acting in downwards direction. Yes, Fazil, two forces. Yes, good. Another is tension, which is acting in upwards direction. There is no other force on the body. So let's draw the FBD of M, mass M. FBD of M. And I call this tension as C because the name of this string is C. So if I draw FBD of C, so this is mg, which is acting in downwards direction. This is TC, tension, which is acting in upwards direction. So if your system is in equilibrium, then tension in string C is equal to weight of the body. Mass is 10 kg and G is 10 meter per second square. So tension in string C is 100 meters. See, if a body is in equilibrium, that means net force acting on the body is zero. I'm just increasing the number of steps. Just for the sake of clarity, two forces are acting on the body which are in opposite direction. Forces are vectors. To add forces, one should use parallelogram law of vector addition. But here, since both the forces are acting in opposite directions, so instead of adding them, you can subtract them. So take any of the forces positive. Let's say I'm taking upwards as positive. Body is not moving anywhere. You can take any direction of positive. If I take upwards as positive, then downwards would be negative. If I add these forces, then TC minus mg equal to 0. You will write tension at C is equal to M. You can either use all steps or you can write this as directly that if a body is in equilibrium, then the force which is acting in upwards direction should be equal to force acting in downwards direction. So this is the thing. Tension in string C is equal to 100. Okay. Now let's consider this point P. So if we consider point P, then three tensions are acting over it. One here, it's TA. One here, which is TB. And one here, which is TC. So if we consider point P, then three tensions are acting over it, A, B, and C. So if I consider point P, FBD of P, so if this is P, then this is your tension TB. This is your tension TA. And this is your tension TC. So this is TB, this is TA and this is TC. See, if this angle is 37 degree and I take a normal here, then this is again 37 degree. They are alternate angles. So I can call this angle as 37. This TA is acting along x-axis, TC is acting along y-axis, but this TB is not acting along any axis. So it's better to resolve this TB. Angle is given with respect to y-axis. So along y-axis, the component is TB cos 37. I'm just dividing TB into two parts. And along x-axis, component is TB sine 37. Upward force is equal to downward force. You can write that your TC, which is acting downwards, should be equal to TB cos 37. If I consider equilibrium along y-axis, you can substitute the values. You know that TC is 100, TB is unknown, but you know the value of cos 37. Cos 37 is 4 by 5. So this is your TB. It's how much is this? 25 into 5, 125. Similarly, if I take equilibrium along x-axis, so your TA is TB sine 37. So your TA is TB. TB is 125. Sine 37 is 3 by 5. So 5 2s are 10, 5 5s are 25. So TA is 75.